Welcome to Chapter 6. Chapter 6 continues our discussion of probability distributions. In this case, we're going to talk about the continuous distribution, sort of an extension from what we talked about before in the discrete distributions, except that we're not going to allow ourselves to have at-value probabilities. So, what are we going to do? Well, we're going to continue our discussion about what is a random variable, in this case, continuous. We're going to interpret the probabilities associated with them, first with the continuous uniform distribution, and then we'll move on to the normal distribution, which is by far the most common distribution we'll encounter in our daily lives. We'll use the standard normal table and then into Excel. We're an Excel class, so we use Excel to solve those problems and start looking at probabilities of variables that follow the normal distribution and see how those things work themselves out. So to start, let's see how this could be used. Let's say you know the manager of a small sushi restaurant in Arizona, and this lady's trying to estimate the daily amount of salmon that is needed. Now, she's estimated the daily consumption of salmon is normally distributed. So over time, she's probably seen this data and modeled it so that she could see it as a histogram and saw that it's mound-shaped. And from there, she realized historically that, well, the consumption's about 12 pounds with a standard deviation of about 3.2 pounds. But she'd been buying 20 pounds of salmon every day, and it's resulted in a lot of waste. So what she wants to do is buy enough salmon to meet the daily demand of customers on 90% of the days. So based on this information, she'd like to calculate the proportion of days that demand for salmon was above her earlier purchase of 20 pounds. It could be a small amount. Calculate the proportion of days that demand for salmon is below 15 pounds. So before it was above 20, now it's below 15. And determine the amount of salmon that she should buy every day so that it meets the demands on 90% of the days. Great. How do we get there? Well, let's start with the original discussion, random variables. Remember, we're going to randomly assign a value. We're going to see it in an experiment, and that value can vary. Discretely, there's countable or countably infinite number of values, but what's interesting about it is I can assign a particular value to an outcome, and known within a particular set, all those values, probabilities, have to sum to 1. Now the continuous doesn't allow for us to assign a particular value. I can't say the probability of x equals 6 is something. If you see a continuous distribution, uniform, continuous, normal, t, if the question is what probability of x equals 6, the answer is immediately 0. But what we're looking for, though, are probabilities between a range, because we're going to look at how does a function appear at the top of this values range on a curve. Much like we did in calculus when we integrated between a and b, we're doing the similar thing here, except that we're not worrying about the calculus piece. It's the application of finding area. It's the density, the PDF, the probability density function. Knowing that if we put this function or curve over a range, if we account for all values, that area will be 1. So we know no at-value probabilities, and I think what we need to talk about here is, since we can assign a particular value, can't say x equals x is anything, it's got to be 0. We know the probability that x equals a is 0, probability x equals b is 0 because you're continuous. The probability that x is between a and b, notice we have the equal signs here, so a is less than or equal to x. It doesn't mean anything because you can't equal a. So it's the same as a is less than x. B, well, if x is less than or equal to b, doesn't really matter because you can't have equal, so you could say x is less than b. So there is no distinction between equals and less than or equal to and less than, greater than or equal to, or greater than. So we have to get that out of our vocabulary when we talk about it for continuous. Now, I'll screw up, and I'm sure you will too when talking about it. It doesn't matter. We just have to realize that the values a and b can have probabilities. They just can't. This is where the PDF comes in. The PDF is that function that we're going to float above a curve. You think about the normal curve, and you've seen it before because you've asked, I'm sure, at least I used to ask, do you curve? Well, you hope the data is normally distributed, having a bell curve to it where it has a lot of symmetry. Well, we know that that line that makes the shape of the bell is our function, our PDF, And that's over all values from negative infinity to positive infinity. And that whole entire area has to equal 1. You can also do it cumulatively. So if I say let's accumulate up to a value, or up to and including a value because there's no difference, big F of x is our continuous random variable. Well, that's the cumulative side when we accumulate up to a value. So if I say let's accumulate up to b, and I say let's accumulate up to a, knowing that a is less than b, if I take f of b minus f of a, that difference is the area I'm interested in and gives me my probability. Much like the complementary rule, now we're taking the entire span of down from the top of what I need, and I take away what I don't need on the low end. That difference gives me the probability in the middle. And you can work up and down into the tails as well. The easiest way to get there is to talk about the continuous uniform distribution. This is by far the easiest. It's often known as the cheese distribution, and we're going to use this probability density function over a range from A to B. So if you think about a rectangle, and along the lower portion of the rectangle across the length, if the lower left is A and the lower right is B, that is your length. Now the height, if we know that the entire rectangle must have an area of 1, the height multiplied by the length from A to B has to equal 1. So if you have B minus A as your length, 1 over B minus A must be your height. That's what we're seeing here. Our PDF is 1 over B minus A for this value, because 1 over B minus A times B minus A, that's the difference between my endpoints, gives me 1. Anything else is 0. Anything. So for this, a better way to look at it is with a picture. So the picture I'm showing is the total area. That area in the yellow is total area of 1. We know A is the low end, B is the high end. The difference, B minus A, when multiplied by the height, 1 over B minus A, gives me 1. So the PDF is this 1 over B minus A. By itself, 1 over B minus A means nothing. And when multiplied by a particular value, it's nothing more than a functional response. It is not a probability. But when it's multiplied by a difference or a range value between A and B, you take the difference. Say there's a value R that's halfway between A and B. If you took R minus A as a distance and multiplied it by 1 over B minus A, that will give you a probability. But by itself, the height is not a probability. It needs to be multiplied by a distance. What we're interested in is the area under the curve. That area under the curve over a particular range gives us probability. Means are pretty simple. We know that the low end plus the high end divided by 2 puts us right in the middle. So if your A was 5, your B was 15, 5 plus 15 is 20, divided by 2 is 10. Standard deviation, we're not actually going to use this, but it's an interesting little formula. You take the difference squared, so that looks normal, right? We're taking the square deviation. In this case, we're dividing by 12. There's an interesting proof out on Wiki if you want to see it. We're never really going to use it other than just an illustrative piece here. More interested in knowing how to calculate a mean. So let's take a look. If I pump out here to Excel for a second, exactly what we've seen before, and I'm just going to repeat the example. Let's blow this up a little bit. So, historical data. Particular cosmetic line follows a continuous uniform distribution. Lower end is 2500, upper end is 5000. And we have that. Here's lower, here's upper. And we know that the height is going to be the difference between 5000 and 2500 divided by into 1. So 2500 into 1. There's our height. So this value multiplied by the difference between this and this is 1. So the mean, standard deviation, well, the mean's pretty simple. You take the low and the high. Standard deviation, you take the square root of the difference, square divided by 12. Pretty straightforward, right? Not difficult. If I want to know what's the probability that sales exceed $4,000, X is greater than 4,000, I'll take the height and I'll multiply by the difference between, since it says exceed 4,000, 5,000 minus 4,000 times the height, and you get a 40% chance of that happening. If I wanted to say, what's the probability that you're between 2,500 and 4,000? It would just simply be the complement to this. Since the entire area is 1, take away the difference of 0.4, and you get 0.6. Normal distribution. The normal distribution, by far the most common. It's symmetric or bell-shaped, as you see. It has a lot of symmetry to it, and if you drew a line down the middle, well, half will be on the left and half will be on the right. And where do we see this? Everywhere. Heights and weights of folks, SAT scores are one, debt is another. Lots of things occur naturally and normally. And all of our inference that we'll draw in this class, particularly, will be from the normal distribution. And as we see it, the low end, we cut it in half since it's symmetric, 50%. Upper, 50%. So the mean, median, and mode all line up. If the mean's in the middle, the mode would be the highest or most, and now the median's in the middle, so it's symmetric in that way. It's also asymptotic in that this line here will never ever touch the black line on either side. So you can get close to but never touch the floor. That's the asymptotic piece. However, here, the normal distribution is completely described by two things, mu and sigma squared. So the mean and the variance completely describe what's happening with the normal distribution. So like all other distributions or anything we've come in contact with, we want to calculate means and variances right away. However, it's not so easy to calculate this PDF as it was with the continuous uniform. It's this convoluted, they call it the most beautiful formula, and it is when you solve it, but it's rather difficult to solve with an integral. We'll just use the assumption that it can be solved and then use Excel to get us there. What we have to worry about, though, is that not two distributions are always the same. In some cases, they have different means. In some cases, they have different variations. What we have to do is think about how do we get from taking the means and the variances and standardizing them. And we'll do that by taking something called the standard normal distribution, where we're going to take whatever the mean value is, find the value of x in the middle, subtract the mean, divide by the standard deviation, and get a z-score. Sound familiar? Z is x minus the mean divided by sigma. That value will set us in the middle and will give us a z value of 0. Once we get to 0, we'll talk about unit jumps of 1, meaning the standard deviation of 1, where the probability below 0 is 50% and the probability above 0 is 50%. Now there is a standard normal table. Excel gives us a greater opportunity for precision instead of having to interpolate in values. What's nice about the normal distribution is the symmetric piece and the ability to use our empirical rule allows us to get a lot of quick estimates without even doing a lot of math. Knowing that when we're at the center, 0, anything below it, or below and including 0, remember it's continuous, or above 0 or above and including 0, is going to be 50%. So what does it look like? Well, we know we can get z-scores, and z-scores put us on the path to standard normal. Let's just assume we were able to calculate z-scores. Pretty straightforward. How do we do this? Well, what we'd like to do is say, I'd like to know the probability that z is between 1.96 positive and negative 1.52. So what I'll do is I'll find the probability that z is less than 1.96, and then I'm going to subtract away the probability that z is less than negative 1.52, knowing that 0 is in the middle. So the difference between looking back down on 0 from 1.96 and down on 0 from 1.52 negative is the probability that you're in that range, 91.07%. You can do it easily in Excel using the norm.s.dist function. Let's take a look. So if I start off by figuring out how to do a few pieces here, start here at the top. We're going to figure out how to do this by first taking a look at the norm.s.dist using the true function. True means a cumulative value. So 1.96, and we're going to subtract away the negative 1.52. That difference is 91.07%. That's the easy way to do it. Looking up in tables, well, that's what I did, and a lot of you probably already have done. The easiest way now is through Excel. What I'd like to then show you now is how do we calculate the value for z when we know the probability? Well, let's just say that we need to find out what's the probability of something of value z when it's equal to, say, 68.08%. Well, what I have to do is use the inverse function. And the inverse function for us is going to be norm.s.inv of 68.08%. We just saw this. So it gives us a value, a z value associated of 0.47. Does that make sense? Well, if we know z of 0 is in the middle, meaning 50% is below and 50% is above, we know that that z has to be greater than 0 just a little bit. So it makes sense that z of 0.47 is a value just above 50%, or say 68%. And that's what we did here. Norm.s.inv, that's the normal distribution for the sample, and I'm taking the inverse. Remember, dist is probability, inv gives us the output. This gets us to the empirical rule, because remember I was just describing to you, well, I knew it was a little bit above 0. Remember, within one standard deviation either way, about 2/3 of observations fall, 68.26%. Within 2 deviations, 95.44. Within 3, 99.72%. So we can use this idea that if your value of, say, z is outside of 1, it puts you into the upper, say it's 32 in total, 16 here, 16 here. You're in the upper 16%, lower 16% when you're outside the interval. As you can see, when you get farther and farther out, when you get a z-score greater than 3, you're way out in the tail. You're almost considered not almost believable. That's when you become an outlier. So we know 1, 2, and z be 3. Anything outside of 3, that's where outliers form. Make sense? Let's look at a couple of different examples here. Let's just say you have an investment strategy with a expected return of 4% and a standard deviation of 6%. Let's just assume that the returns are normally distributed. What's the probability, knowing that you have a return average of 4%, deviation of 6%, what's the probability of earning a return greater than 10? Now, if the mean is 4, the deviation is 6, 10 is 1 deviation higher than 4. So 1 deviation above is 10. 68% of all observations fall within 1 deviation. So that means 32%, as I just showed, are outside that range. You're pushing yourself into the outer 32. So if I look at it from a direct math standpoint, what I'd like to do is do the conversion of 4 being the mean to 0, and I'll do that with the normal distribution transformation to standard normal. What's the probability? Well, what we find is that if above 10, since I want to know the probability of earning a greater return than 10%, that would be 1 deviation away, putting in the outer 16th percent. Make sense? That's a quick back of the envelope trick. I knew where the cutoff line was 10%. I knew where the mean was. The center was at 4%. I had 1 deviation on 6%. Now I'm into the outer and upper tail. So that's the upper 16%. So you want to know what's the chance of being there? It's upper 16%. That's the symmetry and the symmetrical property that we can use and the empirical rule to get us back of the envelope answers. But let's just get back to where we were with these z-scores. I can take any x and convert it back to that z value of 0, having a standard deviation of 1, and quickly solve these problems. It's called the normal transformation. So we know that we're looking for values on either side, and it gives a good sense if your probability is above or below 50%. If you're above 50%, you're going to be to the right of the middle. If it's below 50%, you're going to be to the left. So we want to be able to calculate those particular probabilities or values if you're given probability, so that we can figure out the solution to these complicated problems of, say, inventory management. So the inverse transformation, even though mathematically all you're doing is reverse solving for the z distribution, that value x can be done by the norm.s.inv. So taking a look at the management aptitude test is a good way to start. It's normally distributed, mean of 72, standard deviation of 8. What's the chance that a probability randomly selected manager will score above 60% or above 60? So I want to know, with the mean being 72, a value of 60 is to the left or below 72, what's the chance a manager will score above 60? So he's going to be looking up on a lot more values than he could look down on. So I'm going to do a z transformation, 60, 72, and 8. That gives me a z-score of 1.5. I want to know the probability z is greater than 1.5. Well, if I know the probability of z greater than 1.5, great. The problem is all the standard normal tables are look back, so it's all 1 minus a particular value. So 1 minus a particular value gives us what we need. So I'd like to be able to convert to z. So now what I have is a value of x being 60. That's the number where randomly selected manager is going to use as the cutoff. Mu of 72. Sigma of 8, the z-score was negative 1.5. That 1.5, I'll then go into Excel and use that norm.s.dist function. But since I can't look upward in Excel, I have to look backwards in Excel. I have to take the complement to the z greater than 1.5 negative. So I want to know 1 minus the look back. And that will be a very large probability, 93.32. See what we're doing here? So with that in mind, that will help us solve that initial problem we talked about when people are trying to do inventory management at a seafood place. So with all that done, I use the complementary rule looking back. Very simple to do. Back to that final case we just saw. Can we solve this problem where we're buying the right amount of salmon for this little restaurant, where the daily consumption is normally distributed with a mean of 12 pounds and a standard deviation of 3.2 pounds? Well, what proportion of the days was demand above 20? Well, 20 minus the 12, which is the mean, divided by the standard deviation, that's the number above. So I would like to know the probability that z is above 2.5. Well, that's way out, 2 deviations above, so it's going to be a really small probability. The problem is I can't use Excel to look up that way. So I'm going to use the complementary rule. I'm going to look down from z all the way down to negative infinity. So 1 minus the probability that z is less than or equal to 2.5, and I get a really small probability. In Excel, to see that done, it looks like this. I have my value of 20, 12, and I get my 2.5. And I'm going to use the same function I just saw before, norm.s.dist. Let me blow this up a little bit so you can see it. Give you a better chance at success with this. Norm.s.dist. Now, that's pretty straightforward. The question becomes then, what proportion of days was demand below 15 pounds? So z less than a particular value. That helps me with Excel because I'm not having to do the complementary rule. So 15 minus 12, divided by the standard deviation. So I get a z of 0.94. That's still above 0, so you're to the right of the line. 15 is greater than 12. So if I want to know below, it's going to be a big number because I know it's definitely more than 50%. So up to 0, z of 0 is 50%. I'm saying z of nearly 1. That puts me almost another more than 30% to the right of 0. That's why it's 82.64. Here in Excel, because it's a little more precise, the answer that we just saw was interpolated with a table. I'm going to do the same thing. The converted value of 0.94, norm.s.dist of true, and it gives me the answer we need. The last one, how much salmon should she buy so she meets current customer demand on 90% of the days? Well, now she wants to know what's the value of z when the probability is 0.9. Well, let's try that. With that value, I need to calculate z. Well, one way to use it to use this formula, 0.9, and I can find 0.9 and work through the probability here. So I know that I have 12 and 3.2. I know that 9 is the value I want, so I'm going to use the inverse function. Norm.s.inv of 0.9 gives me my z value in here, and I solve. I solve using the value, and I say 12 plus 1.28, that's the value I just calculated, times the standard deviation, and I need to order 16.1 pounds. That's a nice thing to know so I don't overstock. I can also use an older formula called norm inv. I put in the probability I want, 0.9. I put in my mean and my standard deviation, and I get the same answer. Either one's fine. This one's a bit easier. If you're lazy like me and like to use Excel to the fullest extent, this one's straightforward and you can use it straight out, but you'll get the same answer. So now we've done a lot with the normal distribution, the uniform continuous. We're going to move into even deeper water next time when we start talking about t-distributions, ultimately chi-square distributions, and f-distributions, all based on the normal. We'll see you in the next chapter.